Before your eyes is the Mumbai Trans Harbour Link, India's longest sea bridge, stretching 21.8 kilometers across Thane Creek. This is a massive infrastructure project worth over $2.1 billion, designed to completely solve the traffic congestion of the Mumbai megacity, cutting travel time between central Mumbai and the satellite city of Navi Mumbai from 2 hours down to just 20 minutes. However, to turn this infrastructure ambition into reality, engineers had to embark on one of the most brutal construction projects. They had to directly face massive technical challenges, drilling foundations into the muddy seabed, battling the constantly changing tides of the Arabian Sea, and dealing with a highly corrosive saltwater environment. Moreover, they had to mechanically calculate how to lift and perfectly assemble solid steel bridge sections weighing thousands of tons right on the water surface with millimeter precision. So, how did engineers reinforce the foundation deep beneath the mud, handle the massive bridge sections, and complete this mega sea bridge? We will explore the detailed construction process right now. Before we begin, if you are passionate about how engineers conquer mechanical marvels, please hit the like button and subscribe to the channel so you don't miss our next technical breakdowns. And now, let's find out how Indian engineers build a 22,000-meter sea bridge in the middle of the ocean. To understand why the Mumbai Trans Harbour Link was approved by the Indian government, we need to look at the deadlock of this megacity. The economic hub of Mumbai is essentially an area bounded by the sea. Along with the economic boom, the transportation system connecting the center and the mainland area of Navi Mumbai is always in a state of severe congestion. Millions of vehicles every day have to take a detour along the coastline of Thane Creek, wasting more than 2 hours. The urgent need is a direct route cutting across the sea to relieve traffic pressure and expand development space. To support this 21.8-kilometer structure, engineers established a colossal foundation system consisting of 1,089 bridge piers. The biggest challenge? The entire route was covered by a thick layer of soft, highly compressible clay mud, a surface completely incapable of bearing direct loads. The construction had to be deployed simultaneously across two fronts: 5.5 kilometers of coastal mudflats and 16.5 kilometers in the deep sea. At the near shore and mudflat areas, the board cast in situ pile method was applied. Engineers used heavy-duty hydraulic vibratory hammers to directly drive permanent steel casings, 3 meters in diameter, through the weak geological layers. These steel casings acted as a mechanical shield, blocking the lateral pressure of soil and seawater, keeping the borehole completely stable throughout the construction process. Inside the casing, the drilling system utilized rotary bits tipped with ultra-hard alloys to break through the geological strata until they locked firmly into the load-bearing basalt rock deep below. Immediately after, the reinforcement cage was lowered, and high-strength concrete was pumped to fill the entire borehole, creating a solid, permanent foundation block that transfers the massive load directly into the bedrock. On the 16.5-kilometer deep-sea front, reverse circulation drilling, or RCD, was applied to battle complex ocean currents. The RCD system crushed the seabed rock while using high-pressure compressed air to create a suction force, pushing the mixture of mud and rock from the bottom directly up to the filtration system on the barges. Once cleaned, steel cages were lowered and specialized concrete was pumped through tremie pipes, forming permanent board piles tightly bonded to the bedrock. Once the foundation took root, the pier construction began. Given the scale, engineers opted for the cast-in-place concrete method to ensure absolute monolithic integrity. In the middle of the ocean, steel sheet pile cofferdams were lowered around the pile groups. The seawater inside was pumped out to create a dry construction environment, From these caps, the reinforced concrete shafts rose, featuring a widened design at the top, forming the characteristic Hammerhead pier. This T-shaped design was not created to slice through water. Its true function was to create an ultra-wide support platform in midair. This platform distributes the massive mechanical stress from the bridge spans down to the foundation system, ensuring stability against the powerful winds of the Arabian Sea. While the standard span between piers is 50 meters, it expands to 180 meters at international shipping lanes. After the 1,089 Hammerhead piers were spread across the bay, the superstructure assembly began. However, a major technical hurdle appeared at the shipping lanes. To allow ocean-going vessels to pass, the distance between piers had to reach a record 180 meters. At this length, a regular concrete girder is too heavy. It would cause structural self-destruction under its own weight before even carrying a single vehicle. The only mechanical solution was orthotropic steel deck, OSD, technology. These are hollow steel box structures, reinforced by a network of longitudinal and transverse ribs. This design is significantly lighter than concrete, yet possesses superior dynamic load-bearing capacity. To install the steel span onto the pier caps in the open sea, instead of utilizing floating cranes, which carry the inherent risk of capsizing under lateral wind pressure, engineers implemented the hydraulic Strand Jack lifting technology. This process utilized a specialized barge fitted with steel lifting towers. Atop these towers is a system consisting of 16 Strand Jack units, each with a pulling capacity of 300 tons. Just prior to approaching the installation site, the Strand Jack system simultaneously retracts the cables, hoisting the multi-thousand-ton OSD block into the air, reaching an elevation that surpasses the height of the concrete pier caps. Once the steel block is safely suspended in the air, the barge activates its mooring winches to move forward with extreme, calculated slowness. The barge advances between the two piers, transporting the entire suspended steel span until it aligns perfectly directly above the bridge bearings. Finally, the hydraulic lifting system releases the pressure to slacken the cables, slowly lowering the OSD block, stabilizing its center of gravity, and resting it precisely onto the permanent bearings on the pier caps, with a margin of error measured in millimeters. With the framework joined, a final material challenge remained: the road surface. Because the OSD steel deck flexes under heavy loads, regular asphalt would crack immediately. The solution? Stone matrix asphalt, SMA, reinforced with polymers. This material adheres perfectly to the sandblasted steel, allowing the road surface to expand and contract synchronously with the steel structure. The project also had to survive alongside nature. The route crosses the Seri mudflats, the breeding ground for thousands of flamingos. To protect them, massive sound barriers and non-reflective lighting were installed, preventing the construction from disorienting the migrating flocks. Even during the global supply chain disruptions of the early 2020s, 15,000 workers consumed 170,000 tons of steel, enough for 4 Golden Gate bridges, and nearly 1 million cubic meters of concrete. The entire length is now embedded with thousands of sensors, monitoring vibration, stress, and wind speed in real time 24/7. From steel casings driven through mudflats to 1,089 Hammerhead piers cast in the ocean and the float-over mastery of 1,400-ton spans, every phase was a physical problem solved with absolute precision. The inauguration of this bridge in early 2024 has rewritten the map of the region, cutting travel time to just 20 minutes. It is not just a vital expressway, it is a mechanical anthem affirming the power of modern engineering to conquer the most brutal environments on Earth.